Um, I'm not sure. Yeah,
Yeah,
answer.
I think that's what he meant. Right, Arnab? Is Arnab there?
I believe he meant part 3.2, number 5.
Yeah, part three, number, yeah. 3.2, number 5. That's what I thought.
Yeah, I'm sorry. I went outside to just get coffee. What were you saying, Professor?
You're saying that you wanted to look at part 3.2, number 5?
Yeah, yeah.
Yeah,
It's just that. It's just the only. I just want to see it as a rough example on
sure.
how you do it. I understand the process on doing it. But like, it's just like I just want to see how you would prefer to like have it.
Correct. No problem.
And then after that, add every single optimization problem that's there.
I'll do my best.
Thank you. Thank you. I
We
appreciate
only
it.
have an hour.
Yeah, we only have an hour. That's right. If you guys want, we can do one tomorrow as well. If you would like, we can do
That'd be
another
amazing.
hour session.
That'd be amazing.
Yeah. So f of x, okay, what the first thing I'm going to do is I'm going to rewrite. I'm going to rewrite it. And how am I going to rewrite it?
Using the like set it to the power rule of like
To
one
the
half or
1/2
something.
power, right? Because I
Mhm.
want to use, like you said, the power rule. So then I take the derivative and I apply the chain rule, right? The chain rule is the big idea because I have an inside function and I have an outer function, correct? So the chain rule states that I put the 1/2 in front, I leave whatever's inside alone. I don't touch it. Then I subtract 1 from the 1/2, which gives me a negative 1/2. And then I take the derivative of whatever the inside function happens to be. And in this case, it's ln x plus x. And then what's the derivative of ln of x? Well, it's 1 over x, right? According to the rule. And then what's the derivative of x?
One,
Derivative is
one.
plus 1. And this whole thing is being multiplied by 1/2 ln of x plus x raised to the negative 1/2 power. And at this stage, we are finished. In terms of finding the derivative, we are done. We are done. Now, if you want to make this a little cleaner, a little more compact, right? We usually don't have negative exponents. Let me just redo that box again. Make that a little nicer for you guys. Right? And so then I can rewrite this, if I would like, I can rewrite this as 1 over 2, the square root, because of this negative, I place it in the denominator, and that 1 over 2 exponent implies the square root. So this becomes ln of x plus x. And I multiply this by 1 over x plus 1. And at this point, you can distribute if you'd like you can distribute this if you'd like, but it's not necessary. As long as you get to this point here, you're finished with differentiating, which is the task or the objective of that particular problem. So you would be good with that. Okay, so that's how I would approach this. This is really just applying the chain rule onto logarithmic functions. That's it. So does that suffice, Arnab? Okay, we're good. Okay, so let's look at optimization. We have plenty to choose from.
Yeah,
Um,
Professor. Sorry about my Wi-Fi. It's kind of delayed. Um,
yeah.
yeah, I understood it.
Okay, good. Good. All right. Sorry for that little spin move there. Uh, let's look at the next thing then. So, Coco, do you have any particular one that you would like to look at? I know you said every single one, but there's a lot to choose from. Um,
Number 4.
Number 4, okay. So number 4, a lot of these are box questions, which are very like they're classic optimization problems. They're like the most classic that exist, meaning that they've been done so many times that it's kind of ridiculous to do them again and again. But yeah, they like these problems. So it says a box with an open top is to be constructed from a square piece of cardboard 10 inches wide by cutting out a square from each of the 4 corners and bending up the sides. What is the maximum volume of such a box? Okay, so number 2, optimization. And look at number 4. Now we have a box, it's constructed from a square piece of cardboard. So that's pretty important. We have a square. We start out with a square. And what do we know about each side? Each side is 10 inches, 10 inches. So it's 10 by 10 inches, right? And then we take this square and we cut out pieces of cardboard from taking a square from each of the 4 corners. So this is a corner. This is a corner. This is a corner. This is a corner. So we're cutting pieces out, right? So we're gonna take away this portion here. We're taking that away. We're taking this away. We're taking this away, and we're taking this away, right? And so then we're trying to create a box. So then we can fold these flaps here, right? We fold these little flaps here. And we can, if you could try to visualize it, we can flap them or we can fold onto those flaps right there, those dotted lines there, and create a box. Now the issue is I don't know how much I should cut. That's the question, right? How much do I cut? So then what do we say? We know for a fact that they're squares. So that means that this side here is X, this side here is X, and so on and so forth, right? These are all X's, correct? And then when we fold the flaps, what do we have? We have something that looks like this. I'm not the greatest drawer here, but hopefully you guys understand what I'm trying to do, right? So I'm trying to create a box, not the greatest box here, but what do I know about the dimensions of this box? Can you guys tell me how long this side is, how long these sides are, how long these dimensions are?
How long it is with the ripped parts?
Yeah, so when you rip it up, right? When you rip up when you rip up,
So
when you
don't
cut
you have to
out
attribute a
the square,
variable to it?
yeah, these are my variables. This is X. So do you understand that
So this is gonna be minus X, 2X.
minus 2X, correct?
Yeah, yeah.
And he said the same thing. So good, thank you. So this is 10 minus 2X. That's how long it is. And then similarly, because it's a square, this other side also is 10, and we also take away X from it on both sides. So that this piece here is 10 minus 2X, correct? And then finally, this piece right here, that flap is X. So then what do we have? We have a volume, right? We have the equation of the volume. What's the volume of a box? Length times width times height, isn't it? But this is the length. This is the width. And this is the height. So then I can replace everything with 10 minus 2x multiplied by 10 minus 2x multiplied by x. That is the volume of my box. And now what do I have here? This is known as a polynomial. This is a polynomial function. And so then the volume is what? When I distribute everything, I get 100 minus 40x squared. So I'm doing that a little quicker because we should know how to FOIL by now. And then this would be, the last portion would be 4x squared, right? And this whole thing is being multiplied by x. So when I distribute it one more time, when I distribute all this here, my final volume function is 100x minus 40x squared plus 40x cubed. So what did I just find? And this is the hardest part, guys. This is the difficult portion of this optimization problem. This is the function to what we're trying to do. We're trying to maximize, right? We're trying to function to be maximized. So I'm trying to maximize this. So then if this is a function that I want to find a maximum of, what should I do after I set up the function?
Set it equal to 0.
I can't set this equal to 0 yet. I need to do something before I set it equal to 0.
Get the derivative.
Derivative.
I must take the derivative first. So then in order to maximize, I find derivative first. That's the first thing I do. So find derivative. The reason why I do that is because eventually I want to set it equal to 0 so that I can find where is it on the graph that I have a tangent line whose slope equals 0, which would indicate either a max or a min. So I want to find the derivative. So v prime of x, this is 100 minus 80x plus 12x squared. And I set this equal to 0.
Do you wanna like reorder those things or no?
Sure, I can reorder it. That's perfectly fine. I can do that. I could do 12x minus 80x plus 100. That's perfectly fine. You can do that. The point is that you differentiated first, set it equal to 0. So now what do I have? I have a quadratic. I have a quadratic function, and I can easily solve this either using the quadratic formula or see if I can factor it. And
Yeah,
this is factorable.
Yeah.
I can factor what? I can factor a 4, looks like,
4.
right? And then I get what? 3x squared minus 20x plus 25. This is equal to 0. And then what do I have to see? 3 times 25 is 75. Are there any two numbers that when I multiply them gives me 75, but when I add them gives me negative 20? So remember how we factor this? We have to
minus 15x and minus 5x.
That's correct. So then I can write this as 3x squared minus 15x minus 5x plus 25. Remember, this is stuff that we've talked about in the beginning of the semester in terms of factoring trinomials. This is one of the things that is expected of you to do, right? So anyways, so then, and then we can factor this by grouping, right? We can factor these two terms here by grouping. So we factor out the 3x and I get x minus 5. Factor out the negative 5, I get x minus 5. This is 4 equal to 0. And then I can factor out, what can I factor out? The x minus 5. And I get x minus 5 multiplied by 3x minus 5, set it equal to 0. And now look what I got. Look what I get. What do I get? I get x equal to 5, and I get that x is equal to 5/3. So I get 2. What do I get? I get two critical numbers. Now, which is the correct one? Is it that I take away 5 inches from each corner to maximize my volume that I create? Or is it that I cut out 5/3 inches on each corner?
5
Which one do you think, without even having to check it, which one do you think makes the most sense?
5/3.
5/3.
5/3, right? Because this is already 10 inches. So imagine cutting half. You're literally cutting the whole box. So actually, if I were to do that, I would be minimizing the volume to 0, but that's obviously not what I want to do. So then just to check, right? Just to check, what I would use is the second derivative. So if I look at the second derivative very quickly, v double prime of x.
Professor,
Yeah.
you see how you got 4 times like just above the second derivative, like 4 times x minus 5.
Yeah.
When you were solving for 0, right? You
Yeah.
got x You didn't factor in the 4 at all?
Pardon me?
Did you factor, like, because it's 4 multiplied by x minus 5. Are you
Yeah.
just doing the x minus 5?
The thing is, that's a good question, right? So you're saying you're multiplying this times this times this equals 0, correct? So
Yes.
we're setting this equal to 0 because it could equal 0. And if it were to equal 0, that means that x would be 5/3. We're
Mhm.
setting this equal to 0, so that means that x could equal 5. But 4 cannot equal 0 because 4 is not
Is 4.
0. It's
Okay.
4. So then you can immediately either divide by 4, which people do, so they just divide by 4 and it cancels out. Or you could just say 4 does not equal 0. So you can't even, there's no point even talking about the
Oh,
4. That's
okay,
why
I
I
understand.
disregard it. I disregard it. And then the second derivative is what? Negative 80, correct? Negative 80 plus 24x, right? This is 24x. So this is my second derivative. And if I plug in these numbers for x, I can determine whether it's a local max or local min by figuring out what the sign of the number is, whether it's positive or negative. So then if I want to check what happens at x equals 5, what would I say? 5, the second derivative of 5, which is negative 80 plus 24 times 5. And if I were to multiply this, I get negative 80 plus what? 90, right? This equals what? 5? Wait, what is that? That's not 90. That's a 120, pardon me. So then when you take negative 80 plus 20, you get 40. The whole point of it is positive. If my critical number is has a second derivative who's positive, that means that I have it's concave up. If it's concave up, that means I have a
Minimum.
minimum. I have a local min, or just a global min. But of course, I don't want to minimize it. And then this is just to make sure what we're doing is correct. So the second derivative of 5/3 equals negative 80 plus 24 times 5/3. Well, obviously, when you do this, what do you get? You get negative 80 plus 40, and this equals negative 40. Negative 40 is negative, which means that what? Concave down, which means what? Local max. Or in this case, it's going to be a maximum. And so we say, what do we say? We say that to maximize. Oh, so we found that x equals 5, cutting each corner with a square of 5/3 inches maximizes the volume of the box. So x equals 5/3. Now I want to find the actual volume. What's the volume again? Length times width times height. So then you have to go, pardon me, you have to go back and then tell me what's going to be the actual length if I were to plug in 5/3. So this will be 10 minus 2 times 5/3. And you got to take this step by step. This becomes 10 minus 10/3, which is the same thing as saying 30 over 3 minus 10 over 3, which equals 20 over 3. So the length is 20 over 3. Thank you. Yes, 20 over 3. And then the width will be the same, 20 over 3. And then the height will be what? 5/3. So now I have 20 over 3 times 20 over 3 times 5 over 3. So 20 times 20 is 400. 400 times 5 is what? 2,000. And then 3 times 3 times 3 is 27. So this will be my volume. And the volume is in inches, right? So this would be inches cubed. And if you want more of a approximated value, let me just get that really quick. So this is 2000 divided by 27. So it's approximately 74.07 cubic inches. Okay. No good. So then you can say that this is my exact value. This is called an exact value because it's represented as a fraction. And this is the approximate value. This is the approximate value. So Coco, is that better?
Yeah, it makes sense.
It makes more sense? Good.
Yeah.
And a lot of these problems are similar in style, where it's a similar approach, similar steps. The hardest part, like I said, is getting to this. Hopefully, hopefully you guys agree with me that this is the most difficult part because after this, you guys have been doing these steps a lot, haven't you?
Yeah.
You've taken derivatives, you set them equal to 0, you found x, you've done second derivatives. You just have to learn how to interpret what those numbers mean when you plug in the critical numbers and such and so forth. And I get my final answer. So that should be number 4. Number 3 is very similar. Number 2 is similar because they're all boxes, right? So numbers 2, 3, 4, and 5 are literally the same style because you have boxes. Of course, they're a little different because 5 includes the cost for making the material. So you're talking about not volume, you're talking about surface area of a box, which is different. So 5 and 5. So number 5 and number 2 are talking about minimizing or maximizing surface area, whereas number 3 and number 4 are talking about maximizing volume of a box. So that's a little different. So great. So we saw differentiating logarithms. We saw optimization. Is there any other optimization
Yeah.
problem you want to go over, or is there something else?
I'd like it if you could go like back to the first test. So applications of derivatives. Just go over like 3.4, 1 real quick.
Application. So from the exam number 1, right?
From review sheet, for exam
Oh,
number
review
1.
sheet number 1. Review sheet
Mhm.
number 1. Okay. So we're going back to review sheet number 1. Which one?
It's under 3.4 and it's number 1.
Oh, 3.4 number 1. Okay. So this is a review sheet. This is review sheet number 1. Number 3.4. Number 1, right?
Mhm.
Okay. So then we have, what do we have? We have a function s of t, which is 0.14 t squared plus 0.68 t plus 3.1, and that's between 0 to 6. T is in years. So t is in years. And t equals 0 corresponds with 1997. It says, what is the sales at the beginning of 1997? So part A, what is the sales at the beginning of 1997? So then what does that mean? That means that t equals 0. And what does S of t represent? It represents
Sales for the year.
sales,
So
right?
so
So
you're
then,
just gonna plug.
so you plug in 0, right? And you get 3.1. So then, what are the sales at the beginning? They're approximately, so at the beginning of
2002.
1997,
Oh, okay. I was reading the
because
question.
t equals 0, right? Remember, t equals 0 means 1997. The sales of DSPs, which are just digital signal processors, the sales of DSPs are $3.1 billion. Because remember, it's in the billions. So $1 billion. And then it tag teams it's a coupled question with meaning the year being 2002. So if you're in the year 2002, that means that the t value would be what? Remember, t represents how many years after 1997. So if you're 2002, you're how many years after
5.
1995? So t would be 5, and then you would do the same thing. You would do s of 5, which would mean you would plug in 0.14 times 5 squared plus 0.68 times 5 plus 3.1. That's what you would do. And then you would need a very good calculator to do that. 0.14 multiplied by 5, square it, and then you're going to add by 0.68 times 5 plus 3.1. And I get 10 exactly. That's pretty nice. So this is 10. So then at the beginning, right? At the beginning of 2002, the sales of DSPs are $10 billion. So that's part one, part A. Part A has really very little to do with the actual calculus, right? This is more of a plugging in into the functions that we're given. Part B, however, is asking you how fast was it increasing at the beginning of 1997? So you have to interpret that as what? When you're talking about a rate of how fast something is going, you're considering what?
The rate of change, so derivative.
The rate of change. So it's the derivative. So that becomes very quickly, that becomes done very quickly. So still the time is 0, but now I'm looking at the derivative. And the derivative here is what? 0.28 t squared plus 0.68. The derivative is quite easy to find, isn't it? We've been dealing with a lot more difficult, complex functions to take the derivative of. But as you can tell, this is one of the simpler ones to do. And now all we have to do is plug in 0. And what do I get? Sorry, this should be t, not t squared, because I took the derivative of it. So then if I plug in 0, what happens?
You get 0.68.
0.68, 0.68. And this is in billions, right? So this is really what? $680 million.
Mm-hmm.
So then what is it saying? How fast was the level of sales increasing at the beginning? So the sales were increasing by,
$680 million.
yeah,
Okay, that's not too bad.
yeah, it's not. The thing is, guys, the thing is that as you climb the mountain, right, and you scale downward, the usually going down part is easier. This is kind of like going down the mountain because you've done this already. But now you're going down again and you're like, okay, how was this again? Oh, it wasn't as bad as I thought it was. In the beginning, it must have been like, oh my goodness, you need me to take derivatives. And now you're like, taking derivatives is a thing of the past in a way, right? Because
Yeah,
you're doing this like nothing. It's like,
it's one
that's
of
the
our
whole point.
tools.
That means that what you've been doing is becoming part of you. Like it's being ingrained into your being in a way. So
Professor,
this is now, yeah,
do you think we could also do like one of these? Like, I'm looking at this review sheet right now. I'm just looking at this tangent line question on D. You think we could do that one too?
sure. Yeah, I mean, whatever questions you guys got, that I'm game for it. And then just to finish this up, it's 0.28 times 5, and then you add by 0.68, and I get 2.08. So again, this is how fast were the sales beginning, were increasing at the beginning. So they were increasing by 2.08 billion dollars. So this, at sorry, I should finish this. At the beginning, sorry, this is part terrible. At the beginning of 1997, and then you say the sales were increasing by $2.08 billion. Someone's at my door for some reason. at the beginning of 2002. Okay? Okay, so then you said you wanted to see a tangent line problem?
Yeah, specifically the 8 over
Rad
the
x
square root of
squared
x
plus
squared.
6x. Yeah.
Yeah.
Okay. So again, this technique, guys, the whole tangent problem stuff is also an extremely important skill for calculus. So calculus, when you learn differential calculus, you have to learn how to do optimization. And one of the other essential techniques is this one, finding tangent lines. That's one of the cornerstones of understanding derivatives. You want to understand how to find the tangent line to a graph. So we have a curve here, 8 divided by the square root of x squared plus 6x, right? And I want to find the tangent line to this curve at the point 2 comma 2, okay? So the first thing I need to figure out is what's a tangent line again? The tangent line is just the equation of a line. Y equals mx plus b. So what do I need? I need m and I need b, right? So how do you find the slope? How do you find the slope? The slope is found by
The
finding
point slope. Well, m equals slope, and if you set it
yeah,
up in
what
the
is the
y
slope
equals
of?
m,
We're talking about the slope of tangent line. What is the slope of the tangent line also known as? What's the slope of a tangent line? It's the
rise over run.
not in this class. That's in algebra 1. That's in college algebra. We're talking about derivatives, right?
Oh
Isn't that
yeah,
what the slope of the tangent line is?
I forgot. Yeah.
No, you can't forget that. That's one thing you can't forget. You can forget everything else. Maybe you can't forget everything else. But you gotta know. You gotta know that this is known. AKA. You guys know about AKAs, right? AKA this, AKA that. Slope of a tangent line, AKA derivative. So I want to find the derivative. That's really what this whole problem is predicated upon. Finding a derivative. Now the question is, how do I find the derivative of this monstrosity here, right? So then what I would do is to, since we have our differentiation rules pretty much, equipped into our toolbox, what I would do is I would rewrite this as 8 multiplied by x squared plus 6x raised to the negative 1/2. Do you guys see how I went from this expression here to this expression here?
Yeah, you use the power like method.
Yeah, I rewrote this as a fraction. So I rewrote the denominator as a fractional exponent, x squared plus 6x parentheses to the 1/2. And then I moved that up into the numerator. So I have to make that negative exponent. Now you say, why do I do this? Because now taking the derivative of this is much simpler than finding the derivative of this. Here, I would have to use the quotient rule. And you already know that formula for the quotient rule is kind of crazy.
Are you gonna access directly on the test to do the quotient rule? Because I thought that was kind of like obsolete. Like you could just use the chain rule more often than not.
Hey, if that's what you think, then so be it. But the quotient rule is not obsolete.
Oh, okay.
It just tends to not be that used anymore because of the chain rule. And I agree with you, but there are going to be situations where it's not going to be as simple as taking the chain rule. So the quotient rule sometimes just bails us out at the end.
Okay.
For this, you can disregard the chain rule, the quotient rule, if you know how to apply the chain rule for this. And I would recommend doing this because now taking the derivative of this is much more simple. I take the derivative by doing what? The power rule, right? Placing this in front, and I get what? 8 times negative 1/2 is negative 4. I leave the inside function alone. And then I subtract 1/2 minus 1 is what? Negative 3/2. And then I multiply by the derivative of the inside, which is 2x plus 6. So this whole thing is my derivative. That's what it is. And of course, I always like to make things a little nicer, right? So then I'm going to write this as -4 multiplied by 2x plus 6. This whole thing is being divided by, I guess I could just leave it like that. X squared plus 6x to the 3/2 power. And then if I want to distribute the top here, distribute here, I get -8x minus 24 divided by the square root of x squared plus 6x raised to the 3/2. All I did was I rewrote it. I'm pretty much done. I'm pretty much done with differentiation at this step. But just to make things a little bit cleaner, because I'm gonna have to plug in a number here. That's the whole problem. I'm gonna have to plug in. So then this would be the derivative, or also known as the slope of the tangent line. But
Professor.
this is the slope of a
Oh, okay, never
tangent
mind.
line. This is the slope of a tangent line for some number, for some x value. But I have a particular x value, don't I? My particular x value is 2. This is the specified x value. So x equals 2. So I need to find what happens when x equals 2. And I just have to plug in. So this is -8 times 2 minus 24. The square root of 2 squared plus 6 times 2. Cube that. And I get -16 minus 24 divided by, this is 4 plus 12. Take the square root of that and cube it. -16 minus 24 becomes -40. This is the square root of 16 cubed, but the square root of 16 is 4. 4 cubed, -40. This equals -40 over 64. Divide everything by what? I can divide everything by 8. 8 is a bigger number. Divide everything by 8 and I get -5/8. So the slope, what is this? This is the slope of the tangent line. You see that? We've just completed the most difficult part of this problem, which is finding the slope of the tangent line, which was to find the derivative of this. But you guys have been doing derivatives that you shouldn't be phased by it anymore.
Mhm.
So now this is the slope of the tangent line. And what is it that I'm trying to figure out again? Not just the slope of the tangent line. I'm trying to figure out the
Equation.
equation of the tangent line. But the equation of the tangent line requires me knowing the slope and the y-intercept, or I can think about the point slope form, remember, of a line?
Y2 minus Y1. That one?
That's right. So it's y minus y1 equals m times x minus x1.
Yes.
The y by itself is a variable. The x by itself is a variable. The y1 is a specific y value. The x1 is a specific x value. And the specific x values here are 2 and 2. So I just have to replace y minus 2 equals x minus 2. And the slope is specified to be -5/8. So in this case, I am finished.
Can you scroll up a little bit, Professor?
Yeah. So this is the slope. Sorry. This is the point slope form of tangent line. Right? And if I want to write this as slope intercept form, I would have to distribute. So this becomes y minus 2 equals -5/8x plus 10 over 8. I add by 2 on both sides. And I get y equals -5 over 8 x plus then 10 over 8 plus 2 equals 10 over 8 plus 16 over 8, which equals 24 over 8, which equals 26 over 8. And then if you divide that by 2, you get 13 over 4. So it should be 13 over 4. And this is known as the slope intercept form of tangent line.
Professor, can you please post the review sheet answer key?
Yeah, I just saw it right now. Yes, I plan to do so as soon as I can. So I would have to actually complete it. Okay.
Professor, are we going to post this so we could refer back to it later?
Correct. I've been recording ever since.
Oh, I'm sorry. I'm new here. This is my first one like review
Oh,
session.
no, it's fine. Don't worry. It's like another lecture, like the way we would do lectures, but I'm not just lecturing. It's
Yeah.
it's
No,
much more like,
thank you. I appreciate this a lot, like a lot.
yeah.
I've been just like going through review sheet like since the morning. I woke up at like 7 and like that's the first thing I did.
Okay.
Yeah.
You gotta put in the work. Everything, you get what you put in. That's what it is. It's at the end of the day. At the end of the day. So guys, we got 21 minutes left for today. If you guys think another round of this would be helpful, then we can do this tomorrow as well. Um, so anything else? So we've done tangent lines, we've done derivatives of logarithmic functions, we've done optimization. Is there anything else that you guys want to see again? Do you guys have some issues with?
Yeah, I'm noticing that like as as we did get like stronger at like derivatives, this early stuff is a lot easier. Looking at
That's always, you know how they say hindsight is 2020, right? When you look back at what you struggled with compared to what you're dealing with now, you're like, wait, that was not that complicated. But that's
Yeah.
always gonna be the case because you're stronger now, you're more capable now. So whatever you had trouble with, it's less. It's less of a burden now. Any other questions?
Can we do one of the first problems? I think the relative extrema, absolute extrema.
Yes. Hold on. I don't know what happened to my. Oh, there it is.
Before we go, I want to look at the how you got the slope for this previous problem, the tangent line.
This one. How did I get it? So do you understand that we first found the derivative, correct?
Yeah, on the top it says the denominator is like parentheses x squared plus 6s to the 3/2. Like you got rid of like the 2 on the bottom. I was just wondering how you got rid of
Okay, okay. So this is okay. So this is from an algebraic step. So just make sure you remember this. When you have a base raised to a fractional exponent, I can rewrite this as the nth root of b raised to the mth power. So the n here, the exponent, indicates the type of radical that I have. This is called the index of radical. And the m here indicates the power. So this whole base here is x squared plus 6x. That's the base. What's my exponent? 3/2. So then if I were to rewrite this using this rule, right? This is a
okay.
rule, then yeah, then this would be what? This would be the index, right, of x squared plus 6x, and then this whole thing is being cubed, correct? But because we use 2 so often for radicals, we just disregard it. And we really just write it this way. So that's why I went from here and I switched quickly into radical form because it's easier to evaluate, right? You wouldn't know necessarily what 16, this here will be 16. You wouldn't know what 16 raised to 3/2 is until you break it down with radicals. Then it's kind of simple because square root of 16 is 4, and then 4 cubed is 64, and so on and so forth. And then you go on your merry way to find the.
Yeah, thanks. I got it. I was just quickly scribbling and I didn't
Yeah.
realize.
Sorry, if I go too fast, just tell me. I don't know how fast
Oh,
I
I was
go.
going too fast trying to copy it.
Okay. But you got everything down now, right?
Correct. Yeah.
Cool. And again, this will be posted on Zoom, so you guys can go back if you need it. And I think you can slow it down or speed it up, I think. Okay, so the next one was which one? Wait, Coco said one, right? She said, what did you say? Absolute
Absolute
max?
max and min.
Yeah, which one? So many to choose from. So the first three, they don't have any specified, uh, intervals.
Number 8.
Number 8, okay, so number 8. So this is our review sheet. Number 3. This is number 1. Abs. Max and min. And number 8. So number 8. Number 8, we have our function h of t is equal to 8t minus 1 over t squared on the interval 1 to 3. So what am I looking for? I'm looking for the max value and the absolute minimum value. And remember, these are like the not as difficult ones because we know how to take the derivative of functions now. And this is really much predicated on taking derivatives. So this is at, and I'm going to rewrite this as t to the negative 2. So when I take the derivative of this, I get 8 minus, this becomes 2, positive 2, t to the negative third power. That's my derivative. And that's it. And then I'm going to set it equal to 0. So then what does this become? So after I set it equal to 0, what am I trying to do? Solve for t, correct? So I'm going to get t by itself. So I'm just going to rewrite this as 8 plus t over t cubed, right? Equals 0. So then this becomes what? 8 is equal to negative 2 t cubed. So then this becomes t. So you guys follow me? I'm trying to solve for t, right? I'm trying to solve for t. Now the problem is that t is in the bottom in the denominator. So I'm going to multiply both sides by t cubed, and I get 8t cubed equals negative 2. Divide by 8 now. Divide by 8. And I get that t cubed equals negative 1 over 4. And I want to get t by itself, so I need to take the cube root. Now the cube root cancels with the t cubed, and I'm left with the cube root of negative 1 over 4. Now you're like, wait, you can't have a negative under the radical. Yes, you can if the index of the radical is an odd number, which it is. And if I were to actually find it, I can actually do so. So I do the third root of negative 1 divided by 4. So I get a number. I get this kind of like weird number, negative 0.629, dot, 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 dot. So again, this is a critical number. I only have one of them. So I only have one critical number. And remember, I'm only trying to look for what? I'm trying to look for the max or the min on the specified interval. So is negative 0.6 on this interval? From 1 to 3? It's not. This is not in the interval. Not in interval 1 comma 3. Oh, if that's the case, then I don't even have to include this. I don't even have to test this because it's a negative number already, and I'm in 1 to 3. So the only thing I could do is to find values on endpoints. Of interval. So then I want to find what's h of 1, and I want to find what's h of 3. When I plug in 1, I get what? 8 times 1 minus 1 over 1 squared, which is 8 minus 1, which is 7. So that's one value. The next value would be 8 times 3 minus 1 over 3 squared, which is 24 minus 1 over 27, which is a number clearly bigger than 7. Right? If you want to really make this into a fraction, this becomes 24. Yeah, make this 24 over 1 minus 1 over 27. Make the same denominator, so I would have to multiply the top and the bottom by 27. And 24 times 27, I don't know what that is, but 24 times 27, 648. So then I get 648 over 27 minus 1 over 27, which is 647 over 27. And if I want to write this as an approximated value, 647 divided by 27 is 23.9. So this is 23.96, dot, 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 dot. So obviously, which one is the minimum on this interval? 7 is, and this will be my max. So this will be my minimum value. This will be the absolute minimum value, and this will be the absolute maximum value.
I think you did a mistake because, never mind. Wait, isn't 3 squared 9?
Wow. Thank you, Coco. Who said that 3 squared is 27? Thank you. That's right. 3 squared is 9. You're right. That was my little mistake here. And then this should be 9 instead, right? And then 24 times 9. Yeah, this is a pretty strange number to get. But regardless, right? 24 times 9, 216. So I really get 216 instead. 216 over 27. This is what? 215. And then this becomes 215 divided by 27. So 7.96. Oh, okay. It's still going to be the absolute max, but not by a lot. And let me just graph this just to give us an idea. So if I want to get this idea, I get what? 8 times x minus, this is the, where is the fraction? I guess you don't need it. And this becomes 1 over x squared. So from 1 to 3, yeah, it's an increasing function. It's just an increasing function for the most part. So it's just going up. So then obviously the maximum and minimum will occur at the endpoint, where the maximum will occur when t equals 3 and the minimum will occur when t equals 1. And that would be the answer. So the number 1, absolute max and min, that's not the complicated topic from the review sheet. Number 3, because it's very systematic. Find the derivative, find the critical numbers, test those critical numbers out if they're in the interval, and then check the endpoints of the interval. Which one is the highest one? Absolute max. Which one is the smallest one? Absolute min. And that's all. We got 7 minutes left. Anything else?
Professor? Professor?
Yes, I hear you.
So I just want to ask some format questions. Just like, so how many questions is the final going to be?
I think it's gonna be. I haven't made up all the questions yet, but it's gonna be very. You should expect something very similar to the exams that you've taken so far.
Because the last one was a lot shorter than the rest of them. But
Was it a lot shorter?
Well, it wasn't shorter. It still took me a long time, but it was less questions. And like seeing as how this is gonna be going through like a bunch of different
Yeah,
like chapters, it's like it's gonna be hard for you to like wedge in every little thing,
of course,
you
I
know?
can't imagine everything. No, of course.
Yeah, so it's like, do you have anything in particular that you want us to like really focus on?
I mean, that's I can't say, hey guys, just look. Um like I said, I feel like I've in a way I've given you the topics already, given the review sheet, right? Look at the review
Yeah.
sheet. That's really what you should base your study approach upon, right? Really, this is what college professors would do. You guys should be able to know, or you guys should be able to figure out what to do. Like that's usually the vibe I've gotten from all my most of my math professors. They just like tell us, you know, just
Good luck.
study everything type of deal, right? But of course, it's a final exam. It's cumulative, but of course, you can't fit in every single thing because it would be an exorbitant amount of questions, and there's a lot of grading involved, and we don't want to get bogged down with grading either. But again, this is a calculus one class, so I'm going to be interested in testing you on calculus particularly, and particularly calculus didn't start with the first few lectures. It started with limits. So then I would really study everything from limits onward. So limits, and then you have everything we've dealt with limits, how to evaluate limits. You should be able to do that basic. Then the next thing is derivatives. That's a big one, right? And everything that comes with derivatives, which is a lot. Differentiating
So
rules.
so there probably won't be a lot of domain work and things like that,
Yeah,
unless
the
it's
domain, that's kind of like,
that's
yeah,
like late
that's
algebra.
not so, like, I'm not testing you on domain because that's something that you should have already mastered, right?
Yeah.
This is more on calculus. So limits is a huge one. That's the first one. The next big one, big one is derivatives and everything with derivatives. Differentiation rules. You have to know all of them. Then what's related with that? Related rates, marginal functions, um, curve sketching, and optimization. So those are like pretty heavy subtopics underneath the umbrella of derivatives. And then you also include, what do you include? Derivatives of exponential functions and logarithmic functions, which we've done at the end,
Hmm.
which is covered in all of the review sheets, review sheet 1, 2, and 3.
What about inflection points in the
Oh,
second
implicit differentiation. That's
implicit
another one.
difference?
That's another
Yeah,
one. Yeah, that's
I
also a
mean,
big one.
I
So
actually like doing that and derivatives rather than like like every other thing that's there.
yeah, derivatives encompasses a whole lot. Calculus 1 is also known as differential calculus. So it's everything about derivatives. So derivatives, there's a lot underneath derivatives, right? There's differentiation rules, that's one thing. There's implicit differentiation, there's related rates, there's optimization, and there's curve sketching. Those are pretty, those are 5 major things that you should know underneath the umbrella of derivatives.
Are we gonna have another session on Sunday? Because I want to ask how to get second derivative test related max
Yeah,
and
all of that. That's all related to curve sketching. Yeah. So
I know how to do the second derivative test. I'm just unsure of like what I do after I get the second derivative.
yeah, so we've used second derivative in one of the problems, right?
Well, yeah, when it comes to concavity, I can tell that, but
Yeah, concavity. That's what second derivative tells you. It tells you concavity.
that's the only thing. There's nothing else other than that.
Well, associated with concavity is point of inflection. But
Mhm.
beyond that, that's all there is. There's nothing
Okay.
more.
I don't know why I thought that there was
Oh,
well because like when
the
we're
second
not doing
derivative tells you.
concavity, one of them says find this function using the second derivative test. Does that just mean just take the second derivative and that's the end of
Yeah,
it?
take the second derivative, plug in the critical numbers, and you would be able to determine whether that is a max or min. That's what the second derivative test indicates.
Okay. Thank you for explaining that.
Yes, Coco. I'll try my best to give you guys everything you guys need for the next 24 hours. Uh, Well, hopefully you guys found this short little review session helpful.
Absolutely.
We can resume tomorrow. Would the same time be okay? 6 to 7, I think. Yeah,
Yeah.
sorry about that. Something came up. It should have been 6 to 7. Thank you for your patience, but
It's better that it's later because it gives us more time to like work on stuff, find
yeah,
where our
it's just I
weaknesses
don't
are.
want to
and
make
stuff
it
like
too late, because that's also
Yeah.
especially not tomorrow, because tomorrow I don't want you guys to be all the way just studying all the way to the wee hours of night when your exam is really early.
Yeah.
So 5, you say, Coco, 5 to 6? Okay.
Honestly,
everything-
I prefer 6 to 7. I'm gonna be staying up real late. Anyway, like
Okay, I'll let you guys know. 5 to 6, or we can do 5:30 to 6:30. How about that?
that's a compromise.
Huh?
I think that's a good compromise.
It's a good compromise, right? We always have to compromise. Everybody's no, then we do this time, then we do that time. Oh, well, good.